We've arrived at the statement for the fundamental theorem of arithmetic. So what is the statement? The statement is, if we have any natural number which is bigger than 1, then it's either prime or it can be expressed as a finite product of prime numbers. And the expression is unique up to reordering, essentially. So if we interpret a product of one prime number as just that prime number, you don't need to say this statement is either prime, or you can just say it can be expressed as a finite product of prime numbers. Generally, people don't like to think about products of just one number, and we take it as a definition that if we're multiplying a number and there's no other thing with it, it's just that one number. So if you accept that convention, you don't have to write is prime, or you can just say is a finite product. So here's some examples to indicate what this is saying. So if we take the number 10, we can write it as 2 times 5, but we can also write it as 5 times 2. So the primes that show up are unique. The order in which they show up is not. So we have to reorder them. But the number of primes that show up, the primes that show up and the number of times they show up is unique. As the next example illustrates, 441 is 3 squared times 7 squared, but it's also 7 squared times 3 squared, provided I did my arithmetic right. So the order in which they show up is not unique. And in fact, we could have put the 3 over here. It's convention to sort of collect powers, collect the same primes into powers like we did here. But we could have done 3, 7, 3, 7. 3 times 7, 3 times 7. That's also another way of writing this. So, the primes that show up are unique. How many times they show up are unique. The only thing that is not unique is what order they appear. So anyways, that's what that statement's about, unique up to the order of factors. And now this theorem actually gives us some insight onto why we might not want 1 to be prime. So this theorem in particular would be false if 1 was prime, because 2 would be a product of prime factors. It's just 2. Or it's a prime number, so 2 is just 2, and that should be the unique factorization of 2. But if 1 were allowed to be prime, we could write 2 as 2 times 1. So now we have 2 different factorizations of 2. We have 2 and we have 2 times 1, but it's worse. We now have 3 different factorizations of 2, because we can also write 2 as 2 times 1 squared. So now we have 1 showing up twice. And we have yet another factorization of 2, 2 times 1 cubed, and so on. In fact, if we allowed 1 to be prime, we would have infinitely many factorizations of every natural number instead of one unique one up to order. So we would have to somehow exclude 1 from our statement in order to have a theorem that makes sense. And so instead, for this particular case, we exclude 1 from the list of prime numbers. And again, it's just helpful to exclude it for this theorem and further theorems and the further theory that we're going to develop.